Morning, everyone. Can you all hear me? Just give me a thumbs up if you can hear me. Okay, thank you. Okay, so we will proceed to our lecture. Okay, so today is our third lecture. Okay, so this lecture is a summary of our previous lecture. So after our previous lecture, you should be able to do the pump impeller size selections based on the given chart. Usually, it will be provided by the manufacturer, and then you will be able to estimate the NPSH to prevent the cavitation. So and then you should be able to estimate performance of the pump in series, which is in series and parallel configuration. So just an estimation based on the given data sheets based on the individual pump. Okay, so today we will proceed to other types of pump. Okay. Okay. So the first type of pump is called the centrifugal pump. So this is a very common pump. So the flow will enter intake. Is a pointer. Okay. So the flow will enter at the center. The flow will enter at the center, and then it will flow up. See, this is 90 degree. Okay. So we say that the flow will enter over here, and then it will be come up over here due to the centrifugal force. So this is the first types of pump. Then the second type of pump is called the mixed flow pump. So this is the flow out is in between the 90 degree and the shaft. So this is the axial flow. So this is the the flow out will be in between. So it could be any angle, not necessarily to be 45 degree. It could be at any angle. Okay, it depends on the design. Okay. And the third types of pump is the axial flow pump. So this is like just like the fan, the table fan that you have. So the flow will go in and out in the same direction. Okay. So remember you have three types of pump. The first type, the flow will go in from the center and come out from the side. So this is 90 degree. This is called the centrifugal pump. and the flow, the air or the fluid come out because of the centrifugal force. The second one is the mixed flow. So partial of it is due to the centrifugal force because it's rotating and because of the centrifugal force, and then it will go to the side. And then another parts of it will be the flow because it will go in the center and it will come out in the same direction as well. That's why it's called mixed flow. And then the third type is the axial flow pump. So the flow will be in and out in the same direction. Okay, so we have these three types of pump. We'll move on. Okay, so the first one, the centrifugal pump. This is a very common pump, as I mentioned. So you can see almost everywhere. So it can be easily identified by their snail-shaped case. So if you look at this, it's like a snail case, a snail-shaped case. So it will have the compression, and then it will have expansion out. So you will if you study the pressure within the case, within the pump, then you will see the difference actually. From one side to the other side, it will expand, and then you will have the centrifugal force and push the flow out. Okay. Over here, it said that you can file all around your home in this washer, the hot tub, the clothes washer, dryer, hair dryer, vacuum cleaner, and so on. So there's lots of usage, and also they use in car, the water pump, in the engine, the air blower, and heater. And so this is actually a very common pump. You use it. Actually, it's used everywhere because of lots of application. And as mentioned in our previous lecture, centrifugal pump usually will be used as a blower. Okay, it will be used as a blower. So what is the characteristic of a blower? Which is will give you intermediate or a medium raise of in terms of the pressure and also the flow. So you will get the intermediate. So it's not the highest flow rate, it's not the highest pressure, but it's at the middle. So it can, because of this, it has lots of usage and application. Okay, so this is the centrifugal pump. Okay, so let's look at some analysis of it. So we'll look at it. Okay, so we'll go into detail. So the impeller or the rotor of the pump. Okay, so you look at this is within the case. So the flow will get in here and then it will come out from the side. So this is the case. And then it actually is within what is called a shroud. So the impeller, and then the flow will go through here like a channel or tunnel. It will go through and then it will spin and it will come here, and then this will be the outlet. Okay. So if you look at here, you need to remember. Okay, you see, you need to find out. Okay, the R1, the radius 1 and radius 2, and then you have the opening B1 and B2. So we will use it to do some analysis later on. Okay, so you need to know this is the R1. Okay, you need to find out where is the R1, R2, B1, and B2. Okay. Okay. So there are three types of centrifugal pump based on the impeller design. So the impeller design, it has a different geometry or different design. The first type is the backward inclined plate, radial plate, and the forward inclined plate. So you look at here, so this is the backward. Okay. So if you look at the design, it curves this way and it rotates this way. So this is what we call the backward inclined plate. Okay. And then this one is like a straight plate. So here you say it's a straight plate. Okay. And then the third types is the forward inclined plate. Okay. The curve is this way, and then the rotational direction is this way as well. So it's in line with the rotation direction. Okay. So the rotation direction is this way, and then the plate is this way. Okay. So if you look at the performance in terms of the performance curve, so the backward it's here. It actually is in between these two at the beginning. At beginning, even this is the same. Okay, for you to know, this is the same capacity. Okay, so this pump has the same capacity, but the plate is different. So you look at these three, they are having the same capacity over here, but their head will be different due to the plate design. Okay, so the radial will have the highest head, then it will follow by the backward, and the lowest head will be the forward. But the forward, the good thing about forward is when it comes to the over here, which is the at a higher flow rate, that it will having the best and the most stable pressure. Okay, over here. Okay, so it depends on your application. Each of them have their own advantages. So if you are looking at the head, then over here this will be your choice. But you are looking at the performance, then or in terms of the capacity, then it will be here. Okay. So this is three types of different pump or different plate design. Okay. Next, we will come to some calculations, some equation. So which is what I mentioned just now, the R1, R2, B1, and B2. So the first one is the volumetric flow rate. Okay, the volumetric flow rate. So uh, this is due to the conservation, the law of conservation. So you will have the inlet and outlet will be the same. So they are constant, whatever going in will come out. Therefore, if let's say there's a change of the B, because it's getting a smaller outlet over here, smaller opening, then the V will be higher. Okay, would be higher. Okay, because you have the R will be higher as well because the R is big. So you need to do the calculations. So when the B is smaller, then the R getting bigger, the V could be getting bigger as well. So it depends on the B opening. Okay, so by using this, you will be able to calculate what is the V out. Okay, the V out. This is a normal. V out normal to the opening, to the outlet. Okay, so that you can find out what is the V out. Okay. We will do one example later on. So this is the equation, and this is just to show you some vector analysis on the flow. Okay. Next, we will look at the equation to find out the torque. So this is the shaft torque by using the equation. Okay, so you have the rho, which is the density of the fluid. You have the volumetric flow rate. Then this is the R1, the radius, the velocity. This is the tangential velocity. Okay, tangential velocity. And you have the shaft. This is in alternative form of the equation. Then with the thought, you will be able to find out what's the brake horsepower, have the omega, which is the rotational speed. Okay, then you will be able to get the brake horsepower. Then from there, we'll move on to the next equation, which is the net head. Okay, so you have the net head 1 over g to gravity, the rotational speed, the radius, and the tangential velocity. Okay, if we will move on to the example. Okay, so one centrifugal blower rotates at 1750 RPM, and air enter the impeller normal to the plate at 0 angle. 0 degree, okay, and exit at an angle of 40 degree from radial. So you have the angle, the alpha 2, so it's here. So as sketched in this figure, so the inlet radius is R1 equals to 4 cm, and B1, the inlet width is B1 5.2 centimeter. The outlet radius R2 is 8 centimeter, and the outlet plate width is 2.3 centimeter, and the volume flow rates, or the volumetric flow rate, is 0.13 meter cube per second. Okay, so you have ideal case, which is 100% of efficiency. So now you need to calculate the net heat produced by this blower in equivalence to mm of water. You just need to convert, because from the calculation you will get the head in A, because we are having the A. This is actually used for A. Then you need to calculate the required brake horsepower in watts. Okay. So we will use the equation we have gone through just now. Okay. So the first equation, the volumetric flow rate. So this is what we have seen just now. By using this, you will be able to calculate what is the normal velocity. So the normal velocity is 9.947 meter per second, and then the first angle is 0. Okay, so you will be able to get the second, the outlet normal velocity, which is 11.24 meter per second, and then you need to calculate the tangential velocity, which is the V2 tangential. So you can use the first velocity, and then you have the angle which is given. Then you will be able to get the tangential velocity, which is 9.435 per second. Okay, now you will be able to calculate the head. So this is the equations that we have seen just now also, the head. So you have the omega, and then this is equals to 0, because the tangential is equals to 0, the 0 degree. So you will be able to find out what is the head is 14.1 meter. Okay. So these two equations actually is the same equation you see here. So you have the equations. First, you will use this velocity, the volumetric flow rates, these equations, find out what's the velocity in normal, okay, the normal velocity. Then with that, you will be able to calculate what is the tangential velocity, okay, because the angle is given. My screen is blurry. It's okay. Okay, I have uploaded the sorry, because there's some technical issue, so I just uploaded the slide before the lecture. So you can download the notes. If let's say my screen is blurred, then you can look at your own lecture notes. You can split your screen into two, so you will be able to see the notes and my screen. Okay. Because I think the blurry might due to the network bandwidth is not stable, or not enough in the internet speed. Therefore, the screen will be blurry. Okay. So I can't control the bandwidth sometimes, because the internet is from the supplier. Okay, from Wi-Fi. Okay. Okay. So it's very straightforward. You just use the equation. Okay, the equation from here to calculate what's the velocity, the normal velocity, okay, at the outlet, and then you can convert the normal velocity at the outlet to tangential velocity. Then you use the tangential velocity to find out what is the head, the net head. Okay, the net head. Okay, so with that you will have the net head. And now, because the questions ask you to convert the head in water column height, meaning it is to just to change from A to water. Okay, so it's very straightforward. You just need to have the density of air divided by the density of water, then you times with the given or the estimated head 14.1, then you will be able to get the in water. Okay, the of water, which is 17 of water. Okay. Then you need to predict the brake horsepower as well. Say that also calculate the required brake horsepower since your pump is 100% efficiency, so there's no need to worry about the efficiency. You just need to continue with the calculations, the brake horsepower. Okay, so the brake horsepower, you have the density of air, the gravitational acceleration, you have the flow rate, even volumetric flow rate. Then you have the calculated head, okay, which is 14.1. This is for A, because you are now referring to the pump. Okay, this pump is for A, or this blower is for A. So you use the density of A, then the volumetric flow rate, and the head, the net head of it. Okay, so 14.1, so you will get 21.6 watt. Okay, so this is for the centrifugal pump. And next, we will move on. Okay, we will move on to the design. Okay, so over here you see two different designs. Okay, design A and design B. So for design A, you see there's 1, 2, 3, 4 blades. Okay. But for design B, there are many blades. Okay, so both of them are not the best design for centrifugal pump. Okay, you need to be optimized. You need the number of plates need to be optimized. If you have 2 liters of it, you have 1, 2, 3, 4, then you will have lots of losses. Okay, you will not be able to push or to pump the air efficiently because you have too many gaps in between. Okay, so you only have 4 plates. However, it's not good to have too many plates also. When you have too many plates, you will look at this design, you have too many plates, then the space or the gap in between is too small. So when the gap is too small, it will cause what we call the flow blockage as well, because when it turns fast, when this propeller spinning fast, then it won't be able to capture lots of air to be pushed forward. Therefore, this is not a good design as well. Therefore, in terms of design, you need to really look at it and check what would be the optimum number of plates. Not too little and not too many. Okay, so this slide is just to show you not to have too many plates and not to have too little plates. So you need to have an optimum number of plates. So you need to do the design and put into the software to do the simulations and to find out which one will be the best. And other than plate, the case will play a very important role as well. So if your case is too huge or too far away, I mean, the cage cannot be too big and cannot be too it cannot be too big actually. So if you're too big, then actually you won't be able to capture or to suck in or to push the air, the flow as well. So there are many factors actually. So number of plates is just one of it, and then the second one will be the casing. The casing, I don't think I have anything here to show you, but I think when come to the next types of pump is about the casing as well. So the case will play an important factor. So when in future, if you have an opportunity to design the plate or the pump or to design the centrifugal pump, then on top of this number of plates, you need to consider the size of your case as well. Okay, so we will move on to the next one. Okay, so next we will move to a second type of pump. So this is the axial pump. So this pump actually is quite similar to your fan, I mean to the ceiling fan or to the tabletop fan. Um, the one that I'm referring to is the normal types of table fan. It's not the Dyson fan. Okay, so because Dyson fan actually is running a different types of propeller, so or impeller. So we wouldn't look at that at this point. So the axial fan, the axial pump actually, the plate and the principle actually is quite similar to your the ceiling fan or the the table fan. It's just that the plate design might be slightly different. Okay, so for this one, the axial pump, if you look at it, this is over here. It said that it's not using the so-called centrifugal force because the working principle is different. So when you have a plate like this, like just like the wing of the aircraft, so it will create a lift. Okay, because of the airflow on the top and the bottom of the plate is different. The pressure, because of the pressure gradient, then it will create a lift. So this is this mechanism actually used, like for example, the helicopter. So it will create what we call the downwash and create a lift for the helicopter to lift the helicopter up. Okay, so the helicopter is spinning the blade, but for aircraft, they are using their wing. Okay, they're using their wing, they're creating a thrust to push the aircraft forward and to create a lift on the wing to lift the whole aircraft. Okay, so this is the axial pump fan. We'll move on. Okay, so okay, imagine turning rotor plane vertically. Now we have a propeller. So you have seen two different terms. Okay, so at over here, I think you have seen two different terms. Okay, so the first one you see is the impeller. Okay, when you look at here, you have the rotor or the impeller, you have the centrifugal pump, and then we talk about the impeller, and then we talk about the impeller design, get the design of the impeller. But now when we move on to this second pump, suddenly this propeller comes up. Okay, so can any one of you tell me what's the difference between the impeller and the propeller? Can you guess what is the difference? Why suddenly when we come to the axial pump, then this term propeller comes up instead of impeller? I think I see no response so far. Okay, it's okay. Okay, so if let's say we are in class now, it is a physical class, then probably I will be able to ask a few of you to give me the answer. However, because of this online class, this is quite two-way interaction. Sometimes quite okay. Propeller open space. Please check on the chat box, the chat room. Okay, so I just now I saw one. It says here it propeller. Wait, check on the Hey, where's my chat room? Where can you type to everybody? Because I think I can't hear already. Because I'm using two devices. One is for because I just do not want to affect the network for one device. That's why I'm using two devices at the moment. Okay, I can't see already. So just now I saw one answer, which is the propeller for open space. Is it correct? Okay. Okay. So actually, the main difference between impeller and propeller is the impeller actually is to use to move the freight. Actually, both are moving the freight actually. Okay, but for impeller, it's more specific, like the what we discussed just now for the centrifugal pump. The impeller actually is used to move the the freight, just meaning to pump. Okay, to pump. And propeller uh, actually is like the impeller as well. But the main difference or the uh, main objective of having this propeller is to have the is to get the how to say the functions or the to achieve the objective to propel. Okay, so you're propelling something. When you are propelling something like a propulsions, like to push and move, then that's the propeller. Therefore, when you look at this side or the helicopter or even the aircraft at the front, so actually this propeller are giving a thrust, they're giving a thrust to move, yeah, to move the helicopter. Therefore, this is called the propeller instead of impeller. Actually, in terms of the design or the plate actually they are similar because some of the thing are not some of the case they are not moving as well, like the fan. So it's just like this axial flow fan. It's just a fan. So this in this case, this this could be referring to impeller instead of propeller. For the helicopter, yes, because it's giving a thrust, it's pushing the or is lifting the helicopter. So that one is referring to propeller. Okay, so this is the difference between the impeller and the propeller. Okay, so if you look at here, this is a real propeller. This is really a propeller because this is giving a thrust or giving a force to move and to lift the aircraft. And then for this one, this actually is the fan. This is also a axial fan. This axial fan actually is like the one you use for your kitchen, for your bathroom, for your PC, because you need to have the cooling for your PC. I'm talking about PC, the desktop. I'm not referring to your laptop because your laptop is using a centrifugal fan instead of a axial fan. Okay, so for your desktop, yes, for a desktop PC, behind your CPU, behind your desktop CPU, you are using a cooling fan, which is a axial or ducted axial fan. Okay, but for your laptop to cool down your processor, to cool down the processor of your laptop, you are using a centrifugal fan. You are using a very tiny, not a tiny lah, a very small centrifugal fan. It's a very thin and small centrifugal fan. If you have a chance to open up your laptop For example, you want to open up to replace your hard drive, uh, regardless normal hard disk or a solid state hard disk. So you will be able to see the cooling mechanism or the cooling system of your processor. Then you will be able to see the centrifugal fan. It's a very thin. I'm talking about like 5 mm in terms of thickness, and in terms of the dimension, could be just like 5 cm times 5 cm, and the 5 cm times 5 cm in terms of the dimensions and the thickness is about 5 mm, or even thinner than 5 mm of centrifugal fan as a cooling fan for your laptop cooling system. Okay, so this ducted fan is like this. You have the axial fan, and this duct, in terms of the case, is very, in terms of the design, is need to be very precise as well. Because if the gap between the impeller and the case is too big, then you won't get a good efficiency, and you won't get a good flow. You need to be very tight. I'm talking about just like 1 mm of gap over here. So I'm talking about the impeller and the case or the duct is just like 1 mm or less than 1 mm away, the gap between the impeller and this case. So then you will get a very good flow. Okay, you will get a good flow. Else your flow, you will be very less, or the performance won't be good unless you will spin like your RPM go to like thousands of RPM, then probably will get a good flow, but in terms of efficiency it's not that good. Okay, so this is a ducted fan. Okay, so if you look at here, this is actually a design of a rotor plate or propeller. So this is the impeller of the propeller. Okay, so it is, okay, you can call it impeller or propeller. That depends on your usage. Okay, as I mentioned, the usage of the impeller and propeller is slightly different, although you will have the airflow, but in terms of the usage, it will be slightly different. Okay, so if you over here say it's a well-designed rotor plate or propeller plate has a twist, so it will twist. You will have a different angle, or if let's say you want to refer to the aircraft, then you will call it the angle of attack. But so over here, this is called the angle, the root angle. This is actually the root angle is close to the hub. Okay, you have the root angle, and then when it come to the tip, then you have the tip angle. Okay, so this root, when it come to the hub, this angle actually is bigger than the tip angle. Okay, this root angle is bigger than the tip angle. There's a reason for it. If you have a good design, you said a good design, you will have a different angle between the root angle and the tip angle. This is because the speed is different. Not saying that rotational speed is different. The rotational speed is always the same. Okay, because you have the RPM. The RPM will stay the same from the root till the tip. But there's one thing is different, which is the tangential speed will different. Okay, it will increase when the radius increase, meaning that when close to the root, the tangential speed is lower than the tangential speed of the tip. Okay, therefore, if you want to have a good design, then you will need to get this thing different. Okay, because when you have different, then you will create, because when you have different angle, you will create a different pressure. Okay, when you have a different angle, it will create a different pressure. But that depends on your velocity as well. Okay, okay. I repeat another time. Let me repeat. Okay. When the angle different, okay, the angle, a bigger angle will give you a bigger pressure. or if you're referring to the lift, it will give you a higher lift. But that depends on your speed. Okay, when you have a speed, when you have the same speed, when you have same speed, when you have a bigger angle, then it will give you a bigger pressure or a bigger higher lift or a higher drag. Okay, so when when the tangential speed is different, okay, from the root to the tip, meaning that if let's say you are having the same angle, you are having the same angle, meaning that if let's say you are having the same angle from the root until tip, and you are having the same angle but different tangential speed, meaning that from the root until the tip, your plate will experience different types of pressure. Let me repeat again. If there's no twist, if there's no twist, if from the root until the tip, they are having the same angle, and and when they rotate the root from root until the tip, they will experience different pressure because the tangential speed are different. Okay, so we just try to like split up this 1, 2, 3, 4, 5. Okay, you have this 5 cross-sectional area. Okay, you have this 5 cross-sectional 1, 2, 3, 4, 5. If this 5 cross-sectional area, they are having the same angle, the same root angle, when they rotate these 5 plates, they will experience different pressure if their root angle are the same, if their angle are the same. It's 5, 1, 2, 3, 4, 5 point. Therefore, a good design, a good or a well-designed rotor plate, they will have this different angle. And when the angle different, they will the pressure will change. Okay, if let's say the speed is not the same. Okay, so over here, if let's say a well-designed, usually when they're having this design, when the tip from the root until the tip, so they will twist, and then when they rotate, when they will have actually they already do the calculations, so the tangential speed will be different. 1, 2, 3, 4, 5. They have 5 different tangential speed over here. So they will try to minimize. The pressure difference. Okay, when you have the angle getting smaller and smaller, so meaning that you will get a smaller drag, and smaller pressure. So meaning that from the root until the tip, it will have a quite uniform pressure instead of one point is higher than the other point, because that will be not good for your plate, and it might spoil, or it might so with this change, you will get, let me repeat again, with this angle change, you will get a quite uniform force or pressure across the whole plate, the plate length. Okay? Yeah. Okay. So that's the design of the plate. Yeah, I will move on. Okay. So this axial fan or axial pump, okay, if you put it in the duct, as I mentioned just now, the duct, or this is the ducted fan. So there are 3, this is just give you a 3 example or 3 types of configuration. Okay, so the first one, if you just have the fan or the impeller, the fan, then it will give you a flow with the swirl at the back because of the rotating of the impeller. Okay, so to reduce this swirl at the back, then you can have two impeller. Okay, you can have two. So even it rotate in in opposite direction, but you still will have the same pumping direction. Okay, meaning that their plate is in opposite direction. So if you look at here, this plate is in this direction and the other one, the plate is in this direction. So meaning that when they rotate, even they rotate in different direction, the flow will still go in this direction. Okay, the flow will still go in the same direction. Okay, but it will reduce the swirl or the vortex at the back. Okay, and the third way of reduce or to change the flow condition is to have what we call a stator at the back. So the stator will have a plate to divert to have to make the direction correct. So to have this what we call the stator and a plate to make the flow at the back here become straight again. Okay, no more vortex or swirl at the back. So this is a third setting. Okay. Okay. So far, any questions on this centrifugal and axial pump? No. Okay. So I will move on. Okay. So I have 10 more minutes. Okay. I move on to the last part of this pump, which is the okay. So so because we can't sometimes when we do the design, we want to design, for example, we want to design for them. We want to design for one whole city. We want to have a pump or a system for the whole city, but we can't really build it to test it out. Because in planning, you can't have the huge pump, you can't have the huge system to test, but you can test it in a small system. We always will scale it down to do the testing before we really put it into the practical, into the project. So if let's say that's the case, then the scaling law is very useful because you will scale it down to do the testing and to verify and proof of concept before you use it in a bigger scale. Okay, so if let's say that's the case, then these equations are useful. So these are the dimensionless parameter and dimensional coefficients. Uh, this is the formula to calculate to get the coefficients, and this is for the capacity coefficients, the power coefficients, and the MPS dash coefficients. Okay, so these are the coefficients that you can use. Okay, when you do the test for the small pump, and then you want to scale it up, then you need to make sure that your big system, the scale up system, will have the same coefficients because they are sharing the same coefficients. This is a dimensionless coefficient. For sure, there's some correcting method to find out what's the error and correction and do the corrections, but we will talk about that later on. But this is just the coefficients for you to scale up and down for your system. Okay. Let's move on. Okay. So for example, you have the pump A and pump B, the bigger pump A and a smaller pump B. So if two pumps are geometrically similar, so if you look at it, it's just bigger and smaller, so they are similar. So these are the independence and independence coefficients or parameter you can use, okay, to scale up or scale down. Okay, because they are, you see the Q, the capacity, the Reynolds number. This is the frictions factors and the C, the H, the head, and power. Okay, so So if you put it here, so this is just a overall summarize of the pump in similar family in the same family. So you can just have this thing this a general curve to present them. Okay. So next will be the pump specific speed. So this is actually is for the pump selection. Okay. So this when you have all these coefficients, or you have the numbers for the for example for this one is in US unit and the other one is in the European unit. So if you let's say you have the RPM speed in different unit, then you will be able to use this to do the pump selection. Okay, if let's say you know a motor, for example, you already have a motor selection. Okay, so this is pump specific speed is mainly for the pump selections. Okay, we will look at examples. Okay, so this is just some conversion to find out. Okay, so for example, if after you do the calculations, this is for the European unit, US unit, the normal unit. So you will be able to calculate and get the suggestions like which pump will be the best. Okay, the centrifugal mix or the axial pump will be the best for your application. Okay, okay, let's look at the example. Okay, so okay, so the first example, so the pump is being designed to deliver 320 gallons per minute of gasoline at room temperature, and the required net height is 23.5 feet. Okay, and then it's rotate the pump shaft is rotating at 1,170 RPM. So so all here is in US unit. So therefore, we'll do the calculations to find out what's the most suitable pump. Okay. So in terms of US unit, this is the US unit. Then you have in US unit is 1,960. So if let's say you want to normalize, convert to normalize unit, so the normalized specific speed, you just do the conversion by using the equation, which is here, or using the ratio given. Okay, then you will be able to find out what's the specific speed. Okay, so it's 0.717, and you look at the graph, you look at the chart, so which is the most suitable one. So for the US unit is 1,960, which is somewhere here. If you look at the normalized one, which is 0.7, 0.5, 717, which is about here. So the most suitable type for this application will be centrifugal pump. Okay, so the centrifugal pump, which is here. Okay. Okay. The next one will be the affinity law. The affinity law, again, this is for you to compare or to have both pump, which is similar or in the same family or in the same casing, either the same casing or the same family, or you have the same design, the same size. Volumetric flow rate. So if let's say you have two pump which is similar, okay, at different volumetric flow rates, and then you will be able to, okay, if let's say you pull this VA over here, then with these different rotational speed omega the impeller, then you will be able to calculate what is the new. This is for the head calculation and brake horsepower. You will be able to calculate the
Doctor, I think you are muted.
hello, 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 hello. Okay, so I will stop here. Okay, so not sure what happened. Okay, so
thank you very much. I see you all after mid-sem break. Okay. Yeah. Okay, I think maybe the network problem. Okay. Thank you very much. I see you all. Have a good rest, good holiday. Okay, bye for now.